Good morning dear students, welcome back. I am your physics professor Dr. Nagaraj. So this is the continuation of superconductivity chapter. I have already explained the concept of Meissner effect, type 1, type 2 superconductors, Cooper pair formation and a little bit about BCS theory. So I will continue with the remaining part of BCS theory and then I will try to explain three more concepts, namely Josephson effect or also called as tunneling effect, and then flux quantization, and finally SQUIDS. Okay, so you can expect one full question from this part also. Okay, well, let us come back to BCS theory. BCS theory mainly depends upon what is known as Cooper pair. Cooper pair is nothing but pair of two electrons. Electrons, when they attract each other, I already told you how electrons can attract. They never attract directly, they attract via lattice interaction. So when electrons are interacted through lattice, they form a pair, and this pair collectively will have a charge of 2e, mass of 2me, and a spin of 0. Okay, plus half and minus half, total spin is 0. That is the property of the Cooper pair, and these Cooper pairs will be having energy Eg is equal to 3.5 kb into Tc, where Tc stands for critical temperature, kb stands for Boltzmann constant. I have explained in detail about Cooper pair formation. So dear students, before proceeding further with this video, better you watch my Cooper pair formation video also, that is just the previous one. And these Cooper pairs within no time will increase in number. Within no time their number increases like anything, and all of them will have what is called correlated motion. That means if one Cooper pair is moving like this, remaining Cooper pairs will also move in the same direction. I gave you that bird example. When birds are flying, when they are flying, they all will fly in the same direction. If one bird deviates the direction, all of them will follow the same track. So that is called correlated motion. And even here also we can see such type of correlated motion, and the reason is all Cooper pairs are alike and all of them are explained by one single wave function. So dear students, when it comes to quantum mechanical world, we cannot treat particle as a particle, we have to look at the particle as wave. So here Cooper pair, a combination of two electrons, is described by one single wave function represented by psi. Not only one Cooper pair, all those Cooper pairs formed within no time can be explained by one single wave function. That means one single wave function is equivalent to that bunch of Cooper pairs, and the entire bunch is now acting like one single molecule, which I called as macromolecule. Okay, this is about Cooper pair formation. Now when the Cooper pairs are flowing in a particular direction, right, what is actually resistance? Resistance is nothing but opposition to the flow of current or opposition to the flow of charges. Okay, now Cooper pairs are flowing in a particular direction, and if they collide with the lattice points present over there, they never take that collision as collision at all. That means collision will not deviate there or break them up. So because of the collision, Cooper pairs are not disturbed, because they all have mutual understanding. If one Cooper pair deviates because of the collision, other Cooper pairs also will follow the suit. That means Cooper pairs, collision is not a collision for Cooper pairs. For Cooper pairs, collision is not taken as obstruction. Collision is taken in a positive sense, so that all of them will travel in the same direction, so that there is always uniform motion, so that there is always current, which is nothing but there is no resistance, there is no resistivity. This is nothing but zero resistance state. Did you understand? I repeat, this is the simplest way of explaining zero resistivity. I tell you dear students, it is not so simple to explain the zero resistivity with the help of BCS theory for your level. It requires used a lot of mathematical equations and higher level physics, quantum mechanics. I am just trying to put it in a simple manner so that you can understand it in a better manner. ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, Cooper pairs ಎಲ್ಲ ಹೀಗೆ ಹೋಗ್ತಾ ಇರ್ತವೆ, ಒಂದು collision ಆಗುತ್ತೆ. We all know whenever there is collision, there is a scattering. So electrons will start moving in a different direction ಅಂತ ನಮಗೆ ಗೊತ್ತಿದೆ. But in case of Cooper pairs, that collision is also taken as an advantage. That collision also will be considered by electrons as a support, so that they continues to move in the same direction, so that there is always persistent current. Like how we can explain zero resistivity. So for answer what to write? Just 2 lines you write. Cooper pairs are described by single wave function. They behave like a macromolecule and they travel in a particular direction with the maximum correlated motion, maximum understanding among them. Whenever there is a collision, they will not take the collision as an obstruction. Even due to collision also they travel in the same direction. This is nothing but zero resistance or zero resistivity. So always there exists persistent current. So I have given the background, I have given the explanation. You can frame your own sentence. ಹಿಂಗೆ ಕೂಪರ್ ಪೇರ್ಸ್ ಎಲ್ಲ ಒಂದೇ ತರ ಇರ್ತವೆ. ದೇ ಆಲ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಬೈ ಒನ್ ಸಿಂಗಲ್ ವೇವ್ ಫಂಕ್ಷನ್. ಒಂದು ಮ್ಯಾಕ್ರೋ ಮಾಲಿಕ್ಯೂಲ್ ತರ ಬಿಹೇವ್ ಮಾಡ್ತವೆ. ಕೊಲಿಷನ್ ಆದ್ರೂ ಕೂಡ ಅವು ಕೊಲಿಷನ್ ಅನ್ನ ಡಿಸ್ಟರ್ಬ್ ಅಂತ ತಗೊಳ್ಳೋದಿಲ್ಲ. ಅವನ್ನ ಅಡ್ವಾಂಟೇಜ್ ಆಗಿ ತಗೊಂಡು ಯಾವಾಗಲೂ ಒಂದೇ ದಿಕ್ಕಿನಲ್ಲಿ ಒಂದೇ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಹೋಗ್ಲಿಕ್ಕೆ ಟ್ರೈ ಮಾಡ್ತವೆ. ದೇ ಆಲ್ವೇಸ್ ಟೆಂಡ್ಸ್ ಟು ಮೂವ್ ಇನ್ ದ ಸೇಮ್ ಡೈರೆಕ್ಷನ್. ಆಸ್ ಎ ರಿಸಲ್ಟ್ ದೇರ್ ವಿಲ್ ಬಿ 100% current, 0% resistance. This is one thing. Now coming to Meissner effect. Meissner effect is another important property which we have to explain using BCS theory. What is Meissner effect? Recall, Meissner effect tells you that all superconductors are very good diamagnetic materials. That means they never allow magnetic lines. They expel the magnetic lines. Suppose if this is a superconducting piece, if I apply the magnetic field is thrown away like this. This is Meissner effect. I will try to explain it in a very simple manner, and with what physics you know, with the help of that only I will try to explain the Meissner effect. Dear students, in second PUC you might have studied something about induced EMF. Have you heard of this induced EMF? I hope. Yes, that is sufficient to understand this concept. What is this induced effect? How it is going to explain Meissner effect? I will tell you. See, Cooper pairs are moving with certain velocity inside the bulk material. When you apply the external magnetic field, the velocity of the Cooper pair decreases. Are you getting? Yes. Cooper pair speed keeps on decreasing when you apply the magnetic field. That means the flow is reduced. Whenever we know flow of electron is nothing but current. When there is change in the flow, there will be change in the current also. So, whenever you apply the magnetic field, external magnetic field, speed of the Cooper pair decreases, and hence there will be change in the current. Okay, whenever there is change in the current, EMF is induced. This induced EMF according to Lenz's law always against the cause. Did you get it? Are you following my point? When I apply the magnetic field, velocity decreased, current changes, EMF induced. So applying the magnetic field is the cause. Applying the magnetic field is the cause. EMF induced is the effect. EMF induced is the effect. And according to Lenz's law, effect is against the cause. So effect will always oppose the cause. So that means now the induced EMF inside the superconductor will oppose the magnetic lines. Therefore, magnetic lines are expelled from the specimen. Got it? So I repeat. When external magnetic field is applied, the speed of the Cooper pair decreases. As a result, EMF is induced. That is sufficient. You can skip the change in the current. When magnetic field is applied, EMF is induced due to change in the speed of the Cooper pair. Thus, induced EMF, according to Lenz's law, opposes the cause. As a result, magnetic field is thrown out of the specimen. That means the magnetic lines are not allowed to enter in. That is opposition. So this way, with the help of Cooper pairs, we can explain even Meissner effect also. With this, now I move on to the next concept, that is Josephson effect. What is Josephson effect? It is also called as a tunneling effect. Follow carefully. I take a piece of superconductor. This is one piece of superconductor, maybe aluminium or niobium or tin or some material, okay, in the solid form. I take another superconducting material, right? And then I bring both of them very close to each other, right? Close to each other. I leave a gap of 2 nanometer, less than 2 nanometer, this gap, right? And that gap I fill by means of some insulating layer, right? It is about 1 to 2 nanometers, such a small thin layer, right? So I have superconductor 1, superconductor 2 joined together by means of an insulating layer, right? You know what happens? Now we know superconductor is full of Cooper pairs. Superconductor is full of Cooper pairs, and here onwards we don't look at Cooper pair as a particle. We have to look at the Cooper pair as a wave, right? So inside these waves are traveling, Cooper pairs are moving. Even here also Cooper pairs are moving. Okay, follow carefully. You know what happens? If the thickness of the insulating layer is as small as 1 to 2 nanometer, then Cooper pairs will try to go from superconductor 1 to 2. That means that tunnel ತೂರ್ಕೊಂಡು ಹೋಗೋದನ್ನ tunnel ಅಂತ ಕರಿತೀವಿ. So Cooper pairs tunnel through this insulating layer, and suppose if you put one ammeter in the circuit, ammeter will show some deflection. That means they start flowing in the circuit and show deflection. It clearly shows that without any source of EMF you are getting current. So this is Josephson effect. So what is Josephson effect? When two superconductors are joined together by means of a thin insulating layer about 1 to 2 nanometer, Cooper pairs tunnel through the junction and establish current in the circuit. This is known as Josephson effect. In Josephson effect there are two types. First one is DC Josephson effect. What actually explained is a DC Josephson effect. What do you mean by DC Josephson effect? Dear students, look at the circuit. I have not connected any source of EMF. Still I am getting current. That too single direction current, that is a DC current. This is nothing but DC Josephson effect. So what I explained is DC Josephson effect only. So what is DC Josephson effect? When two superconductors are joined together by means of a thin insulating layer about 1 to 2 nanometer thickness, then Cooper pairs will tunnel through the junction. That is why it is called as tunneling effect. Cooper pairs will tunnel through the junction, establish a DC current in the circuit. This is known as DC Josephson effect. Let me finish off DC and then I move on to AC. Now, if this layer is very small, then current starts flowing, and that current, I call it as IJ, called junction current, is equal to IC, some constant, into sine of phi. Sir, what is phi here? I tell you, actually this is called Josephson junction. Here onwards I call it as Josephson junction. What is Josephson junction? It is a combination of two superconductors and one insulating layer. Okay, see, in Josephson junction I have Cooper pair, that means the wave traveling from one superconductor to another superconductor. See, this is the wave in first superconductor. I have a thin insulating layer. I have another Cooper pair having wave function like this, right? So once this wave enters here, okay, now here onwards I write it as a dotted one. See, between these two there is a gap. See, the first one I write once again, the first one and this one is like this. This is coming that side, right? So it is coming here. I have a junction, here I have a junction. Once it enters in, it may not be overlapping with this, it may be overlapping also, it may not be. If it is overlapping, you will not find any difference, it appears like a single wave. Suppose if it is not overlapping, then there will be this type of wave pattern. That means between these two there is a phase difference. That phase difference is phi, and that phase difference depends upon the thickness of the insulating layer. Okay, so thickness of the insulating layer will decide the phi value, and IC is nothing but critical current, that is nothing but maximum current. Okay, maximum current when sin phi is 1. Okay, that is sin phi is equal to 90. Sin 90 is 1. Well, this is the expression for current flowing in the circuit, where phi is nothing but phase difference introduced by our junction. So this is DC Josephson effect. Are you following? So DC Josephson effect is over. Now coming to AC Josephson effect. I consider the same diagram. Well, here I have two superconductors separated by a thin insulating layer, superconductor 1 and 2. Now I connect this to DC power supply. You know what happens now? Now also there will be flow of Cooper pairs, tunneling of the Cooper pairs, but the surprising thing is current flowing in the circuit. Okay, you put DC circuit, sorry, DC power supply, right? This is the DC power supply, and put one ammeter. You know what type of current it will measure? That means what type of current is generated, you know? It is AC current, alternating current. AC current is produced. Actually AC current at the ಹೇಳ್ಬಾರ್ದು, alternating current ಅನ್ಬೇಕು, AC ಅನ್ಬೇಕು. But by and large everybody is using the same notation or same word. I am also using the same thing. AC current is produced when you connect the junction to DC power supply. That means the DC is producing AC. So DC means a steady current. Steady current is producing steady voltage is producing variable current. Steady voltage is producing variable current. And the frequency of the AC produced, you can show that it is 2eV. V is nothing but applied voltage divided by H, where H stands for Planck's constant. Okay, so this is nothing but AC Josephson effect. So when you don't connect power supply, current is produced and it is a steady current, so it is called DC Josephson effect. When you connect direct power supply, steady voltage when you apply, you get alternating current in the circuit whose frequency is this much, and this is nothing but AC Josephson effect. Got it? Well, I will explain two more points regarding the Josephson effect. Back to this diagram. Dear students, even though there is no power supply, I am getting current. That means there must be some EMF. No, there must be some EMF, and that EMF, I write it here. Actually, whatever I write is connected to this. That EMF is, we can show that, is directly proportional to rate of change of current flowing in the junction or flowing in the circuit. Please recall, you already studied this type of equation in PUC. You must write some constant, you know, that is V is equal to L into di by dt. Of course, you have to put negative sign to represent the Lenz's law. I just ignore negative sign. Come on, tell me what is this L? Yes, you are correct. It is nothing but inductance. Andare Josephson junction is also behaving like an inductor. So it has got its own intrinsic inductance value, right? Yeah. So Josephson junction is having inductor property, inductance value. That is one thing. Next, so Josephson junction has got two ends like capacitor. Capacitor plate has got two ends, this end, this end. In between I have insulator. In between I have insulator, that is nothing but dielectric. Similarly, there also I have this end separated by insulator. Okay, therefore Josephson junction also behaves like a capacitor. So remember, Josephson junction has got inductance value as well as capacitance value, and this property of the Josephson junction helps us in the designing of qubits. Okay, well, this is about DC effect and AC effect and the difference. In the DC effect, no power supply is connected. In the AC effect, power supply is connected, and that to steady power supply is connected. That steady power supply gives you AC current of this much frequency. And Josephson junction is a combination of two superconductors with insulating layer, and it acts like inductor as well as capacitor. Okay, this property helps us in designing the qubits. This is one thing. Now let us move on to the next concept, that is nothing but flux quantization. Okay, it is flux quantization. What is flux quantization? Already we know Meissner effect. Whenever you apply the magnetic field, the superconductor will throw the magnetic lines out of it. Okay, this is in the case of solid sphere or disc or lamina, something like that. Instead of that, if I take a superconducting ring, so in this form, this is say aluminium ring, this is a superconducting ring. Okay, now I will do one thing. I keep this ring in the magnetic field. So this is the ring, I keep this in the magnetic field. Assume the temperature is greater than critical field, T is greater than critical field. So all the magnetic lines will penetrate through the specimen. So they will go like this. Okay, so this is a normal behavior. paramagnetic behavior, that is when temperature is greater than critical field. Now you keep on reducing the temperature. Once the T becomes less than Tc, that means when the material converts into superconductor, you know what happens? Look at this diagram. Reduce the temperature below Tc, right? And then take out the magnetic field. Don't keep the magnet there. Take it out. Suppose if you keep it there, this type of bending will occur. Now do one thing, take out the magnetic field. When you take out, the magnetic lines which are outside the ring will vanish. But what happens to the lines which are inside? They get trapped in the gap, that is in the ring. That means the lines will be trapped. They will not vanish. And not only that, once they get trapped, they will form their own circuit over there. So they will take this shape. This straight line will vanish. That means the lines, see the lines which were entered in, okay, which were entered in, now they will curl, they will curl around the superconducting ring. So not only they are trapped, they are curling around the superconducting ring when temperature is less than Tc and external magnetic field is removed, provided there is a cavity inside. Solid frame ಆದರೆ ಏನಾಗುತ್ತೆ, magnetic field is thrown out, that's all. Halo ring ತರ ಇದ್ರೆ this type of trapping occurs. This is called flux quantization. So why it is called as quantization? Quantization, as we know, it is nothing but definite amount, quantization of energy. But what that word quantum has got to do in this particular example or in this property? Yes, there is a reason for calling it as quantization. You know, whatever the magnetic lines they get trapped will be actually equal to integral multiple of h divided by 2e. We can show this, h divided by 2e. It may be 1 times h by 2e, 2 times, 3 times, in general n times. And this entire h by 2e, we write it as phi naught, right? That means magnetic flux, the lines we call as flux, number of lines per unit area is called as flux. Magnetic flux trapped in the superconducting ring is always quantized. That is why it is called as flux quantization. I hope you got it. And total flux trapped is always equal to n into phi naught, where phi naught is called 1 fluxon. And we can show by substituting h value and e value, we can show that fluxon is equal to 2.16 into 10 to the power of minus 15 Weber per meter square. Dear students, just substitute h value, that is 6.62 into 10 power minus 34, e value, that is 1.6 into 10 power minus 19, you will get this answer. That means whenever you apply the magnetic field, they will enter. Now you reduce the temperature and withdraw the magnetic field, remove the magnetic field, then magnetic lines they get trapped within the superconducting ring. This phenomena is called as flux quantization, trapping, flux trapping. Why it is called as quantization? Because the number of lines or the total flux trapped within the ring is always integral multiple of phi naught, hence it is called flux quantization. Each phi naught is nothing but fluxon, like photon we call it as fluxon. So this is another property or another concept what we are supposed to remember regarding the superconductor. See, all these things are used, all these properties are utilized in designing certain devices. Superconductors are already finding applications, but not in a larger scale, but in a limited scale. Already we are using superconductors, okay, and these properties are used to detect magnetic field. Very small amount of magnetic field we can detect, and use it to measure voltage. Very small amount of voltage we can measure. Use it to identify the some minerals which are present in the earth crust, or ore we can detect. Okay, geologists they make use of superconductors, and we can use these superconductors to check whether there is any crack inside the material. That is called non-destructive testing. Like you take X-ray of your hand to check check the cracks in the bone, you can check the cracks inside the material with the help of superconductors. Okay, so superconductor properties like flux quantization or Josephson effect or tunneling effect, all are utilized in various cases. Okay, but in order to see the application of superconductor, we shall discuss one important device is called SQUID. SQUID is a short form of superconductor quantum, QU stands for quantum interference device. I repeat, superconductor quantum interference device is known as a SQUID. In SQUID, once again, there are two types, namely DC SQUID and RF SQUID. RF SQUID is also called as AC SQUID. Okay, first I will explain what is this SQUID, and it is going to be DC SQUID only. First, whatever I explain, it is actually DC SQUID only. So I repeat once again, SQUID stands for superconductor quantum interference device. Okay, well, coming to DC SQUID. DC SQUID consists of two junctions. What junctions? Yes, Josephson junctions. This is one junction, this is another junction. Right, so I have two junctions and these two junctions are joined together. So that way, this side one superconducting material, this side another superconducting material. Okay, this whole thing I call as one, this whole thing I call as two. Right, so I just represent the superconductor this side by, okay, let it be. And this is one junction, this is another junction. Right, so this is a two junctions device. This is two Josephson junction device, that is nothing but SQUID. Well, now I call this as junction P, this as junction Q, and this point I take it as X, this point I take it as Y. I connect a battery between X and Y, that means I connect a DC power supply between X and Y. Got it? Okay, now what happens? Current starts flowing from the DC source, it arrives here. Once it arrives here, it divides into two parts. One part goes like this, I call it as I1. Another part goes like this, I call it as I2. So two currents are flowing, and then finally they enter here and then enter here and then merge here and proceed onwards, and that you can measure with the help of ammeter. Okay, now do one thing, apply the magnetic field. See, into mark represents magnetic field applied perpendicular to the board. This already you studied in PUC. The symbol meaning you know. Cross mark is something which is towards the board, dot mark is something which is away from the board. So this whole arrangement I am applying the magnetic field. This arrangement is nothing but SQUID. Now come on, explain what is SQUID. SQUID stands for superconducting quantum interference device. There are two types in SQUIDs, namely DC SQUID and RF SQUID. DC SQUID consists of two Josephson effects. The diagram is as shown in figure. It consists of two superconductors, superconductor 1 and 2 junctions are formed P and Q. Between X and Y, a DC power supply is connected, and the whole arrangement is subjected to perpendicular magnetic field. Total magnetic field is constant as of now. Right? Okay, now follow carefully. When the magnetic field is applied, it will introduce the phase difference between I1 and I2. I1 and I2 phase will change. As a result, Cooper pairs will arrive with the different waves here, and the wavelength is the same but the phase is different. When two waves of different phase fall one above the other, what happens? There will be interference. So interference takes place. Okay, it may be constructive or it may be destructive. Here interference means mingling of Cooper waves, combination of Cooper waves. Cooper pairs, once they form, they start flowing in the circuit and finally they give the current. They will give the current of IR. Cooper pair means it is nothing but flow of charges. Whenever they flow, they constitute current, and that current IR, I already mentioned in the previous case, that is Josephson effect. IR is equal to, IJ is equal to, actually I wrote it as IJ is equal to IC into sine phi, where phi is the phase difference introduced. Okay, now I write the resultant current. The resultant current is equal to IC, that is some constant current, into sine of, dear students follow carefully, pi, right, into phi divided by phi naught. See, there are too many phi's. Please don't get confused. Okay, just to avoid the confusion, I write this phi for time being as a theta. Theta is a phase difference. Phi is not phase difference. Phi is actually flux. Phi is flux. Phi naught is fluxon divided by pi phi by phi naught. This is the equation. We can prove this equation, but not necessary. Look at this equation. Whenever the applied flux change, phi naught cannot change, it is already constant. Whenever the applied flux changes, the whole equation will change, so that IR also will change. So IR becomes maximum or minimum depending on the phi value. Maximum when the constructive interference takes place, minimum when destructive interference takes place. And by conducting this experiment, we get a graph something like this. This is IR divided by IC, and this is phi divided by phi naught, flux by fluxon. You know the graph, how it looks like this? It looks like this. Please look at the graph. It is almost similar to intensity distribution in a Young's double slit experiment. Please recall from your second PUC, when two waves moving towards the same point interfere, when Young's double slit experiment, this is one slit, this is another slit, one wave, when they interfere, it produces bright fringe. One wave, another wave, when they interfere, they produce bright or dark. So the Young's double slit experiment napka ide alva? Same way even here, instead of wave, real wave, light wave, we have wave associated with Cooper pair. So some Cooper pairs are pushed in this channel, some Cooper pairs are pushed in this channel, and between them there will be, initially there will be some phase difference because of the junction. In addition to that, by applying the magnetic field, I create the extra phase difference. Because of the extra phase difference, I will have constructive, destructive, constructive, destructive, constructive, destructive interference. Got it? So by measuring this value or this value or this value, I can calculate phi divided by phi naught. Okay, phi divided by phi naught I will get from the graph in the on the answer birthday, let us say some x, thereby phi, I continue here, thereby phi is equal to x into phi naught. X I get it from the graph, phi naught is already known, phi I can calculate. Sir, what is this phi? If phi eni heli nodana, it is nothing but applied magnetic field. Applied magnetic field, how much you are applying, that you can calculate. Sir, why sir we have so many devices to find the magnetic field? Why you need squid? What is the advantage of this squid? Hold your breath. This squid can measure very, very thin magnetic field, very small magnetic field, up to the order of 10 power minus 21 Tesla. Such a small magnetic field it can detect. Sir, where do I produce such a small magnetic field? You know, in our body there is magnetic field. Magnetic field is produced by biological currents. Whenever blood flow produces magnetic field. There is magnetic field in your heart. There is magnetic field in your brain. Any small variations happens in your brain due to blood clot or nerve pressure or weakening of the nerve or damage of the nerve due to accident, there will be anomaly in the blood circulation. Whenever there is small variation in the blood circulation, corresponding magnetic field also changes. How much change occurs? Very small change occurs, about 10 power minus 20, minus 17, minus 18, like that. If you can detect such a small variations in the magnetic field, easily you can diagnose the body, or you can diagnose your heart. Any blockages are there, any veins are joined together or entangled together, any clot is there, all these things you can identify with the help of SQUID. SQUID is therefore a beautiful and very useful diagnosing tool. MRI scanning you might have heard, okay, CT scan you might have heard. We are now having what is called SQUID scanning. SQUID is able to detect as small as 10 power minus 21 Tesla. So this magnetic field is produced in our body due to biological currents. Now you got the answer for your doubt. Why SQUID is required? What is the role of SQUID? SQUID is measuring very small magnetic field. How it measures? Just on the basis of interference. See, this is physics. Who says there is no physics in technology? Everywhere, wherever you go, there is physics. And of course, physics is everything. Okay, this is what I wanted to tell you. So SQUID I explained in detail. DC SQUID then I explained what is ಮಾಡಿದ್ದೀನಿ. In my next video I will come back to you with the RF squid, working of RF squid, and then superconductors in qubit designing. There are 3 qubits, namely charge qubit, flux qubit, phase qubit. In fact, this is nothing but phase qubit only. I will once again repeat it in the next video. Till then, goodbye. Thank you very much. Please watch my videos, like my videos, press the like button, and then subscribe to my channel, share the link with your friends. And this particular chapter material, study material, is available in the description box. Please go there, link for study material anta ide, press that link, you will get the PDF of this particular chapter. Okay dear students, thank you once again.